Okay, good afternoon, everyone. So my name's Dr. Troy Dion. I'm a JSPS postdoctoral fellow here at Kyushu University. Because I'm part of JSPS, I thought I'd also give a bit of my background, because part of being part of the JSPS scheme is I'm supposed to increase cultural ties between Britain and Japan. So I'm going to talk a little about my background in the UK. So if you have any questions about the UK or my background, feel free to ask those at the end as well. So I'm going to talk about me, and then I'm going to talk about magnets in everyday life, so devices that we use, places where you might not think magnets are. I'm going to go through the history of magnetism and discuss some of the concepts. So hopefully in discussing these concepts, we'll be able to explain how magnets are used in everyday life. And then I'm going to talk maybe a little bit about current research that I do and that in other fields as well. So I was originally born in Kendal in the UK, and I did my undergraduate at the University of Leeds. I studied physics there. After then, I did a year abroad in Hamburg, just working in a cafe. And then after that, I worked at the Journal Scientific Reports, which is part of Nature. That was in London. And then I did my PhD at UCL and Imperial, both in London. Then I did a 3-month postdoc at UCL in London last summer, and now I'm doing a 2-year JSPS postdoc at Kyushu University. So I'm originally from England, in the north part of England, a place called the Lake District. There's lots of mountains and lakes, and I'm from a town called Kendal. A lot of people have been asking me since being here if I'm not cold, because I'm always not wearing a jumper or anything. And the reason is because the north of England is very cold and very wet, so I'm kind of used to the cold. So Kendal has a rich history. It has a castle, which was built on a hill, which was formed by an ancient glacier which came through. So that was built in the 12th century. And it was owned by the Parr family, who, if you know who King Henry VIII was, the Tudor king who had 6 wives, and Catherine Parr was his last wife, who managed to survive. He notoriously chopped the heads off a few of his wives. So yeah, she was the last surviving wife. So this is the Kendal Parish Church, which is actually the widest church in England. I used to sing here in the choir, and it's 1,200 years old, older than the castle even. So in Kendal we have the only pub where people can go and drink, which is on holy ground. It's the only pub in the UK that's on holy ground. In the Lake District we also have the Hawkshead Brewery, which is very famous in the UK for making beer. This is the Brewery Arts Centre, which is somewhere I used to work when I was a teenager, and it has a theatre where they put on plays. We have this bottom middle picture, we have music, and the Kendal Mountain Film Festival is held there. So that's a place where people come to mainly drink, but also watch films about mountains and mountaineering and other sort of outdoor activities. Kendal's famous for food. We have Cumberland sausages, which are usually in this swirl shape. We also have Kendal mint cake, which isn't really a cake. It's got 3 ingredients. Those ingredients are sugar, water, and mint flavour. But it's very popular with mountaineers. They get a lot of energy from it. And Edmund Hillary, who was the first person to reach the summit of Mount Everest, apparently was eating Kendal mint cake at the top when he arrived. There's also a few famous bands in the UK that originally come from Kendal, so Seven Seals, The Wild Beasts, and British Sea Power. John Dalton, who's a famous chemist, he came up with the plum pudding model, which we now know to be wrong, but he originally thought that the atom consisted of positively charged space with negatively charged electrons that embedded that. So John Dalton, at the age of 14, ran the Quaker school in Kendal with his brother. So quite an impressive person. And this is the coat of arms of Kendal. So these are kind of like thistle plants, which they used to use in ancient times for taking wool off of sheep so they could make clothes. And this is the Latin Panis Nihi Panis, which means wool is our bread in Latin. Kendal's a historic market town, so sheep is one of the main things that was traded back then, and still today actually. So then I went to Leeds University. So Leeds is very famous for its sort of vibrant nightlife. So in Christmas, just running up to Christmas, the shopping street in Leeds called the Hedgerow and Kirkstall Lane actually is the busiest shopping district in Europe. So this big building in the foreground here is actually a shopping centre that got started being built when I first went to university and was only finished as I was leaving. So this is the university in the bottom left. So William and Lawrence Bragg were famous. Yes, I do support Leeds United as well. Someone said in the chat, Leeds United. Yeah, so Sir William and Lawrence Bragg developed the Bragg's law, which is it tells you the distance between. So you have some crystal structure, and you want to know the distance between the atoms. You can fire X-rays onto that crystal lattice, and the X-rays that bounce off the top will have a phase difference from the X-rays which bounce off the second layer, and then this phase difference will give you the distance between those layers given by this d sine theta. So William and his son Lawrence, their lab is now a coffee shop. But yeah, they did their work at Leeds University, and this is me graduating with my grandmother and my mother. So then after Leeds, I went to Hamburg. So in Hamburg, Ernst Ising and William Lentz came up with this Ising model, which is it's a theory in magnetism, which basically connects magnetism with thermodynamics. So then I went to London. I worked in publishing for a year. I worked at Scientific Reports, where I kind of was involved with helping along the peer review process. So people would send in scientific papers, and then it was my job to find an appropriate person who would become the editor for that paper, and I'd make sure that the editor was following the editorial guidelines, and then chasing reviewers to make sure that they had handed in their reviews on time, etc. And then I did my PhD, which was we have this new thing in the UK called Centres for Doctoral Training. So traditionally, when you do a PhD, you would normally apply for funding for a specific project. But these new Centre for Doctoral Trainings, which we have in the UK, they pool a load of money for several PhDs in a certain topic. So the topic that I was involved with was advanced characterization of materials. So it was actually quite a diverse group of people. So there was people doing chemistry, biology, physics, engineering, lots of different subjects, but with centered around looking at different kinds of characterization of materials. And this is my cohort. So I was split between UCL and Imperial, doing mainly work at UCL. So this is my group at UCL. And this is Professor Hide Kobayashi, who's partly the reason that I was able to come to Japan. He had colleagues here with Professor Kimura. So some famous scientists from UCL. We had Sir Francis Crick, who discovered the double helix structure of DNA using X-ray crystallography. And then in electrical engineering, we had Sir John Ambrose Fleming, who came up with the right-hand rule for cross products, which we'll come to later. He also invented the first vacuum tube and was the first successful telecommunications from the UK to America, so making a telephone call across the Atlantic Ocean. And then at Imperial, we have Eric Laithwaite, who basically pioneered the technology that eventually leads to the invention of the maglev train.
This is a coil, and this is a coil, and these three rings are steel rings. They're to help to strengthen the magnetic field. Now, we've found that we can produce this inward travelling field if we make the current in this coil go that way around at the same time as the current in this one is going the other way around. So when we put both coils on together, we can perhaps detect with the copper cylinder a very slight tendency to produce inward travelling fields. That is the bottom of the cylinder moving towards the centre. That's what we're looking for. Now, magnetic field takes no notice of pieces of wood or cardboard or paper, so I can pass a piece of wood underneath without affecting the floating disc in any way. Now, I want you to imagine that we've been able to take this solid structure, put it under a steamroller, and roll it out flat, really flatten it in this direction. And let's try and imagine what that would look like. Well, here's our aluminium plate, and we'll switch it on. Now, there is our aluminium suspended, but not yet movable. I can push it by hand.
Okay, so that was kind of the first research that led to the technology that made maglev trains possible. So here are some objects which rely on magnetism to work. So we've already seen the maglev train. So there's magnets in your headphones, there's magnets in storage devices, even the Earth is a magnet itself. So keep in mind anything that's not on this list that you might be able to think of, because I'm going to ask some questions later, so perhaps you can think of some other things. So what is magnetism? So it's a force and it has a field. So what do we mean by a field? A field is just the action of that force. So these lines that we see here are basically the force that the magnet can exert. So if you were to place iron filings, which are a ferrous metal, which means they respond to magnetic fields, then you get these lines of which follow these magnetic field lines. So magnets are dipolar. So what does that mean? It basically means they've got a north and a south pole. So what do you think happens if I cut this magnet in half? Does it make a north pole and a south pole separated? Will it generate two magnets, north, south, or will it be C, north, south, south, north? Okay, so some B, some C. Anyone going to choose A? Okay, no A's. Good, because this situation would never happen. So when you cut a magnet in two, it will form two more magnets. So we found no magnetic monopoles in nature. And it would actually be B rather than C, because the north wants to align with the south. North is attracted to south, and north is repelled by north, and south is repelled by south. So when were magnets first discovered? So I guess the myth is that in a region of ancient Greece called Magnesia, there was a farmer called Magnus. When he was tending to his sheep, he noticed that the end of his stick, which had some iron attached to it, would stick to certain rocks, which we now come to call lodestones, or which we now know are made of a iron oxide called magnetite. So this is a picture of this magnetite, and this is its crystal structure. But it wasn't until the 1500s where there was a first rigorous scientific investigation of magnetism. So people thought that compasses, which people were using to navigate, would be pulled to the North Star, which is called Polaris. So before magnetism, people would use the stars to navigate, to find where north was. So if you look at the sky, you'll notice that all the stars will rotate around this one star called Polaris, and this basically points you to the north direction. So people used to think that the compass was being pulled by the magnetism of Polaris. But it was William Gilbert in the 1500s who basically said that the Earth itself is a magnet, and when you're on the edge of the Earth, the magnet is being pointed towards the North Pole. So it's the same as those iron filings down here. They will point to the North Pole. If you're here, then you're going to see that your compass is going to point towards this North Pole. And then Carl Friedrich Gauss took William Gilbert's ideas further, did more experiments, and was able to produce a Gauss meter. So instead of just having a compass that points in a certain direction, he was able to measure the magnitude of Earth's magnetic field. So this is an old version, and this is a more modern version which we use today in experiments to measure our magnetic fields. So it was Charles Coulomb in the 1700s who came up with an equation for the force between two magnets. So he said basically the force is proportional to the strength of the two magnets, so M1 and M2 being the strength of each magnet, and it would be inversely proportional to the distance between them squared. So this kind of looks the same as Newton's law for gravity, which is the two masses over r squared. But can anyone tell me what the difference between these two equations are?
Yeah, so I think the difference is that magnetism can be repulsive. Magnetism, it can be repulsive as well. I mean, the force would be attractive between opposite poles and repulsive between similar poles, and gravitational would always be attractive.
Yep, exactly.
Like that.
Yeah, so in this situation they're repulsive, but if we turn this magnet round, now these are going to be attractive. So you actually have to, it cares about the direction that these two magnets are pointing in. If I was to have the magnet this way, we'd have to consider the angle between these two magnets. So we actually need to take the cross product. In this case, we only have a dot product because these are two vectors, right? And this quantity is scalar. Okay, so Hans Christian Ørsted was the first person to notice that there was a connection between magnetism and electricity. He originally did this experiment with a carrying conducting wire and a magnetic needle. So in this experiment, you have some conducting brass rod, and then you have some magnetic needle, so this is basically a compass, and then we have a DC power supply, and we can apply a current to this wire. So can anyone guess what is going to happen to this needle when the current gets switched on? Turning around. Deflect. Okay, should we see? Yes, as the current is increased, there is more deflection. So the compass wants to align with the Earth's magnetic field, but something's happening when the current gets turned on that's making it deflect. So what do you think that is? What's happening here? If you have a current flowing through a wire, you actually get a magnetic field which will rotate around this wire. So if you hold out your right hand with your thumb pointing along the direction of the current, then the direction that your fingers are going shows a magnetic field. So in this case, when you apply a current, you're generating a magnetic field that's going around. Let me go to this view. Okay. So now we have a current which is flowing along this direction. So then we're going to have a field which is at right angles to that. So if the current's flowing this way, you now have a field which is going like this. So it's going this way on top and this way underneath. So presumably the Earth's magnetic field was originally in this direction. So the Earth's magnetic field is pointing this way, which is where this was originally. But now we're generating a magnetic field which is causing the compass wants to line along the strongest magnetic field, and the Earth's magnetic field is quite weak. So as soon as you apply this current, you generate a stronger magnetic field which the compass needle will then align with. So here's a similar experiment, but now we have two wires that are carrying current. So if the current flows in the same direction, what will happen to these wires? So there's going to be a force between these two wires. Is it going to pull them inwards, or is it going to push? Are they going to be pushed out? Play. Okay, so when the current is in the same direction, it generates fields which have a force which brings those two wires together. But if the current is in opposite directions, you have a repulsive force and the wires will push each other apart. So this was demonstrated by André Ampère in France, but then it was Michael Faraday who did many experiments, and he showed, actually let me ask this as a question. If I have a magnet here, which I'm going to move back and forth, and then I have a wire which is wrapped around another magnetic material, and these little red dots are the electrons which are in the wire, which give us current when they move. So what do you think is going to happen if I move this magnet back and forth? Bulb will light up, generate light. Okay, so let's see. Okay, so yeah, as we're moving this magnet back and forth, that's it's generating an electric field which is moving those electrons. So this is basically how electricity is generated in all scenarios, essentially. In big coal plants, you heat up some water using the coal. You burn the coal, it heats up the water, which generates steam. That steam will turn some turbine, which has magnets in it, and those magnets turning will generate electricity in some wires, and then that electricity can then be taken to the grid where it can be supplied to houses or industry, etc. What happens if we have a microphone which has a magnet inside it, and that magnet gets moves every time we speak, and as that magnet moves, it will generate an electric current in this wire. That electric current then is sent down this wire into another magnet which is attached to a speaker. So as music is played, it sends electrical signals down the wire, which then move the speaker with a magnet. So speakers, headphones, anything like that is being controlled using a magnet. Can anyone tell me what this is? It's the opposite of a generator. So what's the opposite of a generator? So yeah, this is a motor. Basically the opposite of this, essentially. Instead of generating electricity, we use electricity to turn a magnet. And the reason we have these holes is because of conservation of energy, when you use an electric field, it produces a magnetic field, but then that magnetic field produces another electric field. But that secondary electric field will oppose the direction of the original electric field. So to keep this moving round in a circle, we actually need to change the polarity of the electric current that we're applying. So that happens every time it crosses this gap, and that allows the motor to continuously turn. It was actually James Clerk Maxwell who managed to theoretically and mathematically put all these ideas together and boil everything down to these 4 equations. And essentially he showed that this change of a magnetic field can generate an electric field, and the change of a magnetic field can generate a current. So we also have these things called electromagnetic waves. Can anyone tell me what this is more commonly known as? So when we have electric fields and magnetic fields at right angles to each other. This is light. Depending on the distance between peaks or troughs, that's known as the wavelength, and 1 over that wavelength is the frequency. And depending on the frequency or the wavelength tells us what kind of light we have. So we have long wavelength or low frequency is radio waves, and then we have up to microwaves, which use to heat up your food or whatever. It's also involved in telecommunications, 5G, Bluetooth. This is all in the microwave regime. And then we have infrared, and then we have visible light, and then we have ultraviolet and X-rays and gamma rays. The wavelengths of these things are comparable to these different things. So you have radio waves, which compare to buildings and humans, and then all the way at the other end we have atomic nuclei and atoms, which, as we said earlier with the Bragg law, use X-rays to look at the distance between atoms in crystals. So now we should be able to explain a few things. We can explain how a motor works. We can explain roughly, I guess, all these things. We haven't gone into too much detail, but we have a bit of an idea now how some of these things work, how compass works. Headphones, same with a turntable. So in the head of the needle of a turntable, as the record spins round and round, the needle moves back and forth on the little grooves within that record, and there's a tiny little magnet in there. So your needle's moving up and down in the same shape as the groove, which then is turned into electrical signals, which then again is sent to a speaker, which then moves back and forth, which generates the sound. So we need to talk about some other concepts to understand these other things. So there's different types of magnetism. So far we've kind of just been talking about magnetic fields and how they interact with electric fields. But where does magnetism come from? Because there's actually many types of magnetism. So if we start thinking about an atom, so we have protons and neutrons in the nucleus, and then we have electron shells. And these electron shells have electrons which we can sort of simplify and say orbit the atom. So you can think of this as a current loop. So if we've seen previously that if you have electrons that move in a loop, you generate a magnetic field. So you can think of atoms as kind of little magnets as well. So depending on how the electrons are filled in these electron shells, you can get diamagnetism. So if all the shells are filled, so you have all these electron shells filled, then you get diamagnetism. And it's very small effect. So if there's no applied magnetic field, your atoms aren't going to spontaneously make a magnetic field when you add them all up. If you apply field, they will try and oppose the field that created them. So that's again from conservation of energy. But if you have a paramagnetic material, so this is where you have unfilled shells. So basically an electron is the smallest kind of magnet you can have. It's basically a magnet itself, and it can point up or down. So in this paramagnetic case, you have unfilled shells, which means you have some electrons which are both pointing in the same direction, so there's a slight magnetic field. So when there's zero field applied, you kind of get this disordered state where none of these little magnets are pointing in any particular direction. So overall, the magnetization is going to be zero. So magnetization is just when you add up all the little magnets and then divide it by the volume of the material. But as soon as we apply a field, they'll all line up along that field. As soon as we take the field off, they'll rejumble back into a random assortment. But there's a couple of materials, so iron, cobalt, nickel, and gadolinium, which are spontaneously ferromagnetic. So even when there's no field applied, they prefer to line up all along a specific direction. And I'm not going to get into the specifics of why this is, because it requires some quantum mechanics, and I don't think we all have the necessary background to be able to understand that, but just know that it's quantum mechanical and it's to do with energy, and for certain materials it's a lower energy state for the magnets to all line up like this rather than be jumbled in a paramagnetic state. Okay, so then there's another concept we need to know about, which is called the Curie temperature. So magnets aren't magnetic above a certain temperature. So if we heat a magnet up, the energy, the atoms will start to vibrate and move around a lot because of the heat. And if the energy exceeds a certain amount, it will overcome the spontaneous magnetization. Here's an example of a Curie engine. So there's a magnet which is pulling the other smaller magnet towards it, but when the candle heats up this magnet, it loses its magnetism and then falls away from the magnet, and as it cools down, it will go back up again. So it does this cycle thing over and over again. Let me ask a question. So if the Curie temperature of iron is 770 degrees, but the temperature of the Earth's iron core is 5,200 Celsius, where do you think the Earth's magnetic field comes from? So the Earth has an iron core, right? And that's the reason the Earth has a magnetic field. But the Curie temperature is exceeded in the Earth's core. It's way too hot for it to be a permanent magnet. Where does the Earth's magnetic field come from? Like before, so it's like an electromagnet. So there's currents of iron moving up. Let's look. The iron, it becomes liquid, and then you have currents which move around. And then, as we saw earlier, when you have movement of these electrical currents, that generates magnetic fields. I said that the spontaneous magnets, right? So they do have spontaneous magnetization, but they also want to be in a low energy state. And there's a way to get into a low energy state by creating these things called domains. So sometimes you might have noticed that your fridge magnets have fallen off the fridge and they don't seem to be working as magnets anymore. And the reason for this is that it's broken up into several domains. So instead of all of these pointing in the same direction, you now have 4 sections which are pointing in different directions. So overall, this isn't going to work as a magnet because this side is cancelling out this side this side is cancelling out this side. So the net magnetization of this is 0. So if I play this... Okay, so if we apply magnetic field, we can remagnetize this. So now we've got rid of all those domains, and now we're applying a field now to the opposite direction. So now we're applying along to the left. You can see as we make these magnets smaller and smaller and smaller, they get harder and harder. And what I mean by that is it takes a larger magnetic field to reverse the direction of it. And what you can also notice is, so as I come back from right to left, you'll see that this one breaks up into many domains because it's a larger magnet, so it can form many domains, whereas, say, this one will not form a domain at all. This one forms just a couple of domains. So the size of the domains that can be formed in a magnet is dependent on the size. The size of the magnet. So these are really small magnets. Basically, it costs energy to make these domains. And if the cost of making a domain is too large, then it will simply rotate with the magnetic field instead of forming these domain structures. You're probably too young to remember mixtapes, but I'm too young to remember them as well, to be honest. They have magnetic domains on them. So this is a microscopic image, and you can see these like blocks of domains of it being either pointing to the right or pointing to the left. You can print what you want onto these pieces of tape by applying a current to this magnet. So this will generate either a right or left depending on if the current is in the positive or the negative direction. And you'll find a similar thing inside credit cards. You can see that there's these domains of magnetization, which similar to a barcode. So in this case, what are these black and white regions? What does that mean? Yeah, ones and zeros. So these are just bits. So we can either have black or white, which will denote if it's a 1 or a 0, or we can have different magnetization. We can write this by applying a current, but if we move this tape along the bottom of this tape head, we'll actually measure a current. So if it's pointing to the right, we'll measure a current in one direction, and if it's pointing to the left, we'll measure a current in the other direction. So we can both read and write with the same tape head, and this is how we can encode information. We can explain a few more things now. We want to be able to explain what's going on here. So there's another thing in magnetism called anisotropy, and this is basically just you can have a preferential direction. So this might come from the crystal structure, or it might come from shape anisotropy. So which of these magnets, if I apply a field along this direction, which one of these magnets do you think is going to reverse first? So it's going to turn from red to blue. People want to vote for which one they think is going to go first. So we've got a couple of ones. Any other guesses? Okay, I guess we'll find out. So we're increasing the field. So it's actually 11. So the wider the magnet is, the easier it is for the spins to rotate. When I say spin, it's just another word for sort of the constituent magnet that makes up the larger magnetization. But essentially, because the spins are able to rotate more, because the shape anisotropy energy is lower, these ones will switch first. So if we go back to these hysteresis loops, we can see. You can see in these cases how the spins kind of rotate around this edge, whereas in these ones they're kind of more like fixed in that direction. So this has higher shape anisotropy, and these have lower shape anisotropy. And it's similar to the domain stuff. So the larger the magnet is, the easier it is to reverse it or create domains within that magnet. So if we estimate this wider, it'd probably start to generate some domain structure. So the way a hard disk works is it has what's called perpendicular anisotropy. So you have some crystal where it's a thin film, but the magnetization wants to point out of the plane. So this will either want to point up or point down. So instead of the tape where it wanted to point along, it would point in plane. In the hard disk, it will point out of plane, either up or down. So you can apply current pulses, and this will generate these ones and zeros in the. So imagine this is spinning, so the disk is spinning round, and you apply current pulses. And again, like the tape head, you can move this along, and this read-write head will pick up an electrical current as the magnetization changes underneath it. One problem with these hard disks is they have this mechanical moving parts. Don't know if you ever picked up an old hard disk, it kind of makes a creaky, or makes a lot of noise, like squeaky noise inside. If you put your ear to it, you'll be able to hear it, and that's all the mechanical parts inside moving. More modern sort of solid state drives use MRAM technology, where you have these bit lines, so you have lots of these current lines, and if each one of these can be a 1 or a 0, depending on whether the top layer is facing right or left. So basically we fix the bottom layer so that it's pointing in one direction. If the two magnets are facing in the same direction, we'll be able to measure a high resistance when we apply a current to it. And if they're facing the opposite direction, when we apply current, we'll be able to measure a low resistance state. So we'll be able to call this a 1 and this a 0. And then the reversal process of that can be induced by applying a large current. So if you want to switch it, you apply a large current pulse, and that will switch the top magnet from being red to go to blue. And if you want to just read a certain bit, you just apply a small current and determine what the resistance is between the top and the bottom layer. So this is a solid state drive which won't have any moving parts, and you can make these much more dense than traditional hard disks. Okay, so far we've talked about static magnetization, but we can also do stuff with dynamics. So we can excite these magnets. So one use of these is MRI scanners. So you have some powerful magnet which is going to apply a large magnetic field to the body, and then you have these gradient coils which will just change the strength of that magnetic field across the body, because then you're able to split up different parts of the body. And then you'll also have these RF coils. Let me go back. These RF coils will generate a oscillating magnetic field. So if you look at the nucleus of a hydrogen atom, which is just a proton, you can basically treat this as a magnet. So before I was talking about spin, so you essentially have, it's this thing called intrinsic angular momentum, which is kind of this quantum mechanical effect. But for our purposes, we can just treat the proton like it's a tiny magnet. So it will respond to magnetic fields in the same way as other magnets do. It has a north and a south pole. And the thing about magnets is when you put them in a uniform field, they actually precess around that magnetic field. So as this movie shows, you see that the magnetic moment will spin around that magnetic field. Just like if you ever have a spinning top, it starts to precess, which means it kind of like wobbles. And the frequency that it precesses is called the Lama frequency. And it's proportional to the field strength. So if I increase the field, it's going to spin faster and faster. If I reduce the field, it's going to spin slower. So for protons, it's in the radio frequency range. So we use a powerful uniform field to which permeates the entire body. And then we use the gradient coils to make this field non-uniform. So this varies it across the body, and this allows the Lama frequency to vary across the body. So it'll be high towards the head because the magnetic field strength here is high, and it will be slow at this end because the magnetic field strength is lower. And this means we can specify a slice along the body. So initially, all your spins are going to be kind of processing at their specific Lama frequencies, and they're going to be out of phase with each other. So what we need to do is apply a radio frequency pulse, and this will get all of these to process in phase with that pulse. So this is resonance. So when these things resonate, we'll be able to measure a large signal. So in MRI, they can, I'll stop the video there, but in MRI, depending on how long it takes for these things to relax back to their initial states, then you can determine the sort of density of different parts of the body and build up these pictures, these MRI scans, and be able to see inside the body. Okay, so it's a bit more simple when you come to ferromagnetic resonance, which is a technique that I use in my research. So because protons are really weak, really small magnets, the signals are quite weak. But with ferromagnetic materials, you have billions and billions of these magnets all together, and they process in phase, and then you can measure quite a large signal. So you can do this with much smaller fields. So you apply a DC magnetic field to the sample as before, and then we apply microwaves at right angles to that field. So then when the microwave frequency is equal to the precessional frequency, you actually measure a dip in power as a function of the frequency. And this is an example of the setup here at Kyushu University, which I've used to do some of my research. Okay, so as I said, FMR is in the microwave regime. So magnets are integrated in technology such as 5G and Bluetooth. So that's another reason why it's important to study magnetism. I'm just going to play this video.
The first experiment for the Cymatics music video is called a Chladni plate. Now, Chladni plate's basically a metal plate attached to the top of the speaker. There's sand on top of the plate, and you play different tones through the speaker. The plate vibrates, which forms different shapes depending on the frequency of the sound.
Well, we blew up a lot of speakers with the Chladni plate. So there was a lot of experimenting around the Chladni plate, primarily looking at how much volume we can put through there, how much sand to actually put on the plate, and the different shapes of plates and what different patterns would be created because of those shapes. But what we were really testing was what frequencies create the most interesting repeatable patterns, because that was a key point. So we ended up playing pretty much every audio frequency through the plate to see what different shapes it would form.
And for most frequencies, it doesn't really do much, but when it hits a frequency that resonates with the plate, it forms a really nice pure shape. So we found out what those tones were, and those were the tones we used to drive the plate in the video.
That's kind of a analogy which we can now apply to magnets. So I do a lot of simulation work, and I can basically simulate a similar thing. So what we can do is we can apply a field pulse which will excite every frequency in these magnets. So these are the same magnets we had before in those hysteresis loops. So we've got fat ones and thin ones. You can think of these as like the strings of a bass guitar or something. So these ones are going to have low frequency oscillations, and these ones are going to have high frequency oscillations. We basically attack it, and we get all the different frequencies, and then we can do what's called a fast Fourier transform, which basically turns the time domain into the frequency domain, and it will pick out those frequencies. So when they applied different frequencies and tones to find specific frequencies where they made these patterns, we can do the same thing here. So we're cycling through the frequencies now, and at specific frequencies, you're going to see specific patterns. Here we can generate these patterns by looking at these frequencies, and we can change the frequency by increasing or decreasing the magnetic field. So these patterns can tell us things about the material. So in the case with the sound and the sand before, that will depend on sort of the stiffness of the card used, the material it's made of. As they said, it was the frequency will determine what kinds of patterns you have. So with this, the patterns are determined by the shape, again, the magnetic material it's made of. So yeah, we can learn things about these magnets using a similar technique. We can also couple magnets together. So this is from my latest paper, where if you have two magnets that are facing the same direction, they kind of don't talk to each other, so they're kind of like uncoupled oscillators. But if we have magnets that are pointing in the opposite direction, we get two different modes. We can have acoustic, where they both oscillate in phase, so they move back and forth together at one frequency, or they move out of phase with each other, and you get this optical frequency kind of behavior where they move out of phase with each other. And basically that generates these gaps, and these gaps could potentially be used for like next generation computing using magnets instead of electronics. We can also, instead of applying the magnetic field to the entire sample, we can choose to apply, say, the field in the very center of a sample and generate spin waves. So in this case, we have some wave which gets generated in the center, and then it propagates out to the sides. And then we can look at the frequency of those waves and the wavelength. So most electronic computer technology is based on transistors, which require you to have electrons moving through your material. And that's kind of like this person trying to run through, like they're going to get very hot and sweaty, and all these people are going to get very hot and sweaty, which is why your laptop or computer gets very hot and why you need to cool it down. But if you imagine using magnets to transfer information, so instead of this guy moving through this crowd to move information from A to B, this person can transfer information through this wave, and none of the people are moving, so it's going to cost a lot less energy to move information around. So this could be a potential solution to some of the energy problems that we face in the modern era. So I work in a field called Spintronics, which is basically, like I said, it's just another word for magnet, essentially. But we see very interesting effects, like the spin Hall effect. So if you apply a current, your electrons can be pointing up. So your electrons are magnets themselves, and therefore the current is going to deflect electrons that are spin up towards one side of the material, and the spin down electrons to the other side of the material. And this effectively generates a magnetic current rather than a charge current of electrons, of electricity. You get a current of magnetism. There's also the spin-Seebeck effect, which is essentially you have a gradient of temperature, and that can generate a spin current. And then there's 2D magnetism, which is a recent field of study, so kind of like graphene, which show magnetic properties. And then there's other exotic magnetic textures called Skyrmions, and they're kind of like these magnetic knots, like those domains that were quite easy to destroy by applying magnetic fields. These things are what's called topologically protected, and that just means it's very difficult. You'd have to apply huge fields to get rid of these things. They're very stable under certain conditions. So these could form ones and zeros depending on whether your Skyrmion is pointing up or down. Yeah, they've been studied quite a lot, and proposals for them to be used in next generation storage devices is. So some other new technologies is reservoir computing, which is like trying to mimic how the brain works. So transistors, you just have ones and zeros, and you try and do computations based on logic of ones and zeros. But with reservoir computing, you're kind of mimicking how the brain works, where you have neurons which are all connected to all the other neurons. And trying to mimic that using magnets. So because magnets connect to each other via their magnetic fields, they're kind of like neurons in a way. They kind of talk to each other. So that's one field of study. So using spin wave logic, so having spin waves which can interfere with each other and generate ones and zeros, and you can build logic devices out of spin waves instead of the traditional transistors. People are trying to find molecular magnets for quantum computing, so using a magnet as a qubit. There's also magnetic nanoparticles, which could be used in medical settings. So you can have a magnetic nanoparticle which attaches to a specific kind of cell. So if you've got some kind of cancerous cell, you attach it to some nucleic acid or something, which will then go to this specific cancer cell. And then you can use a microwave field which will make that nanoparticle vibrate and heat up the cancer cells around it, killing only the cancer cells. So it's kind of a less invasive and safer alternative to chemotherapy or radiotherapy, which causes a lot of damage to other tissues. And this way we can target just the cancerous cells and be able to destroy those cells. This is from 5 years ago. Hoverboards, I don't think we'll be seeing them, because you need a specific kind of skate park and you need to have liquid nitrogen on hand. So I don't think we'll be seeing that anytime soon. Has anyone thought of any other uses? So they're used in power lines for stepping up the voltages. Obviously, I talked about the power generation. So in wind turbines, your wind is turning your turbine, and there's a magnet inside here which generates your electricity. Geological exploration. Can anyone tell me what's going on in this picture here? So this is a picture of the LHC. So what do you think magnets are being used for in this? So at the LHC, they're trying to smash particles together, right? Focus the antimatter. Yep, they're accelerating particles. And they're also, they're also bending them, right? They're accelerating them. Yeah, so they're accelerating them in a circle. They're also accelerating them to get them started. And then they're also using them to detect them. So the detectors are all these huge electromagnets as well. So they're integral in creating the particles, accelerating the particles, bending the particles in a circle, and then actually measuring the particles as well. So they're very important. It can be used, this is very, does anyone know what this is in the middle? Maybe you don't have these in Japan. Yeah. So there's a magnet in here which keeps it clamped together, and you can actually break these specifically if you have a powerful enough magnet. Yeah, to stop you from stealing. And then this bottom right one is a schematic of a Tomahawk fusion reactor. So in this case, the magnets are extremely powerful, which are trying to control the plasma and keep the plasma in this sort of donut shape. Magnets are everywhere and in everything. I, for one, welcome our magnetic overlords. Yes. Yeah, magnets are everywhere, and they're very important, and pretty much modern life wouldn't be possible without them. It generates our electricity. It's in all our devices. Basically all of matter is made of something that is magnetic in some respect. Does anyone have any questions, whether about magnets or anything else?
Yeah, I had just a small question.
Yeah.
So, you mentioned those quite robust magnetic materials, right? The Skyrmions or whatever.
The Skyrmions, yeah.
Yeah, Skyrmions. Yeah, so why are they? So, what is the physical principle that behind the robustness of these particles? So.
It's to do with like topology. So, have you ever heard of the hairy ball theorem?
Yeah.
So it's kind of like that, where you have imagine a ball and it's hairy, and you try and comb it. There's always going to be one place on the ball where there's like a tuft sticking out, because
so like a defect.
Yeah. So that defect can't be got rid of, essentially. So it's basically a similar thing to that. But if you want to know how these textures form, there's two interactions in magnetism which are important for this. So there's the Heisenberg exchange interaction, which I didn't go into, which is the quantum mechanical effect which creates ferromagnetism, and that makes the spins want to point all in the same direction. But there's another interaction called the Jalishinsky-Moria interaction, which wants them to point at right angles. So when you have both of these effects competing with each other in certain materials, it makes the spins want to create these sort of screw-like structures. And then on top of that, if you have a specific kind of anisotropy, it lowers the energy for these states. And typically you need to be in a very small window of field and temperature where the magnet prefers to be in this sort of skyrmion state. But yeah, it's basically a bunch of competing effects of wanting them to be aligned parallel versus being aligned perpendicular that creates these sort of textures, these knot-like textures.
I see.
So artificial sun using magnetic field. Yeah, so the fusion reactors, so the magnets are there to control the plasma and shape the plasma in a specific way that is able to generate a fusion reaction. Are there any more questions? You can even ask me questions about the UK or education that I've been through, anything like that. I'm happy to answer general questions.
Okay, so this might be a weird one, but so do you watch Chris Broad from abroad in Japan?
I don't know what that is. Sorry.
Okay.
What's it
Okay, yeah,
called?
so he's also Chris Broad. His name is Chris Broad. His YouTube channel is Abroad in Japan. So he's also a Britisher who is like
Oh, I do know
makes
who you mean.
videos
Yes.
about. Yeah.
My
Like
girlfriend.
that.
My girlfriend watches his YouTube channel,
Oh,
so I've seen a few videos. But yeah,
yeah.
cynical
He's-
British lad. Yeah.
Yep. I mean, cynical British is like a redundant statement, isn't it?
Yeah.
Yeah. So, yeah. No.
Outer core, yeah. So it's not the inner core; it's the molten outer core. Because the inner core, I believe, is solid, and the outer core is molten, and it's the convection heat currents which generate the obviously the moving of the molten ion, which then generates the magnetic field. So the magnetic, it's an electromagnetic field as opposed to a spontaneous one. So I was kind of trying to trick you by talking about spontaneous magnetism and the Curie temperature before. There's also interesting theories about some animals that use magnetic fields to navigate, which has never been fully proven. There's been no real... they haven't found the mechanism by which they do, but there is lots of examples of animals doing it, and it's seemingly magnetism being the only thing that could explain it. And the problem is that the thing that would be doing the sensing within an animal could be a very small piece within some animal's brain. So it doesn't need to be very big to be able to detect, but we obviously can't find it. Yeah, so this is kind of like some toy models I made of FMR. So there's the ferromagnetic resonance. So underneath I'm basically rotating a magnet, which is making all these kind of process. And then here we have, pause that one. This is kind of a spin wave. So basically generating a spin wave by exciting one of these magnets, and then it transfers information across here. I didn't discuss these in my talk, but I kind of look at this material called spin ice, which you arrange magnets in either a square lattice or this hexagonal lattice. Basically, you get like magnetic frustration, some interesting thermodynamic effects and things. Oh, this is cool. So one way we can reverse this, so instead of applying a field to the entire thing, we can take this AFM tip. So an AFM is basically, it's a way that we look at materials. It's basically a tip which we move across the surface of a sample, and the force of the force is felt from between the needle and the sample can be detected. So you can essentially measure the magnetism, or if it's, you can use van der Waals forces to look at the topology of a material. But if you use like a high magnetized tip and you go across the edge of a surface, you can actually introduce a domain wall like this, and then you get these pair of domain walls which then move to the sides of the magnet, which effectively reverses it. So instead of applying a huge field, you can actually use a magnetic tip to write specific magnetization states in materials. So I was looking at doing this with these sort of one-dimensional what we call magnonic crystals. So these are made up of tiny little magnets in a row, and you can basically create spin waves which then are dependent on how you arrange them. So if green is up and purple is down, you can create these gates. So you see how in this case the spin wave can travel from this left side all the way across, but in this case it gets kind of stopped by this this weird domain thing that we've made. So we can write specific states into these things that will behave differently depending on how we arrange the magnets. Looking at the Spinwave video, is there a sort of cooldown period between sending one wave and sending the subsequent one? Like, does the center magnet need to fully stop oscillating, rotating before it can be used to send another wave? No, you can keep generating waves. You keep hitting it, and you hit it at the frequency that you want it to resonate, and then it'll keep sending wave information. But they'll just be on top of each other, so it's a bit more complicated, I guess.
Thank you for your lecture. It's very interesting.
You're welcome.
It's time, so thank you for your lecture today.
Okay, thank you very much.
Thank you very much.
Have a good weekend, everybody.